We are almost to the promised land here. I wanted to actually show you that SPSS, which is a stat program, can actually do these things out on computer. And I actually wanted to show you what the results would be. So if you want to take a few notes on this, you can. If you put 1, 2, 3, 5, 6, 7 into SPSS, the top table should make some sense. You got a 2 and a 6 for the mean. Notice the standard D's are 1 and 1, standard error of the mean 0.57. And then it actually has table 2, which is new for you. It's called an ANOVA summary table. Notice what it has there. It's got between group and within group, giving us all the same values we just computed. Sums of squares. What did we want for the sums of squares between groups? We wanted a large value because the sums of squares between groups reflects the difference in the means, the treatment effect. So that number is large here, 24. How about the sums of squares within groups? We want that number to be small because that reflects error. In this case, it's 4. Remember, we got the values there ourselves. Degrees of freedom for between groups. Degrees of freedom between groups. You had 2 groups, so 1 degree of freedom. Notice what it says in the next box there. Mean square. Remember we called that a mean square on week 2? Mean square is another word for variance. The variance between groups is 24 over 1, or 24. The variance for within group, 4 over 4, or 1. Remember, variance, the other term, is the mean square, because it's the sums of squares, kind of the average. So mean square, 24 over 1. It got an F score of 24, just like we did. Notice what the computer does that you don't have to do much of anymore. It gives you an F score of 24, and then it tells you the probability of getting this result due to chance is 0.008. In this particular situation, you would simply write out the exact probability. So you would write out for your APA, as I've done there, F of 1 and 4 equals 24. P equals 0.008. That's better than saying P less than 0.05. This result is statistically significant. So that's how you do an ANOVA. If we move down, you can actually see I also ran a paired sample, not a paired sample, an independent t-test for this. Because I could. I've got just 2 groups. The main advantage that you'll see after the first test of an ANOVA is that you can have more than 2 groups, but here we only have 2 groups, so I could do an independent t-test. Notice the t result. T, 4.899. Notice the F result, 24. Any relationship between the two? The answer you should have is yes. If you take that t value and you square it, 4.899, you get the F score. T squared equals F. So we know that if you get any t score, you square it and you get the F score. F's always have to be positive because it's variance. Everything is squared. So t squared equals F. Notice the numerator mean difference is 4. Denominator 0.81. Sig is the same, 0.008. So in this particular case, you could do a t-test, but we're learning how to do an ANOVA. Last but not least for you, I do have a homework problem for you on this. I want you to do an example with no drug being 0, 2, and 4, and the drug group being 4, 6, and 8. If you want to make a graph and just make your own little graph by hand, that's fine. Kind of assess what's going on. See if you can compute the variance between and within groups and get your F ratio. Compare it, see if you can look back and see if it's significant and make a real world conclusion. Thank you all very much for your patience. Thank you. Goodbye.